Now, let's look at how we can design and parameterize a probability model. A parametric model P sub theta should be as close as possible to the true data distribution. If so, the model can assign a probability to any given input x. This can be used in a scenario that the model identifies abnormal input, which has a very low probability. The model can also be used to generate new data by taking samples from the model distribution. There are many choices for the model P sub theta. Classical parametric models use a small number of parameters. For continuous variables, we often use Gaussian or Laplace distributions. For discrete variables, we often use Bernoulli, categorical, or Poisson distributions. We may also construct a model as a neural network, which is often much more flexible to model complex data distribution. Let's look at the 1D Gaussian distribution as a concrete example. The model parameter theta includes the mean, mu, and the variance sigma square. The model density has this bell shape where the center is controlled by the mean mu and the spread is controlled by the variance sigma square. For a multidimensional Gaussian distribution, the parameter theta includes the mean vector mu and the covariance matrix sigma. The mean vector set the center of the model distribution, and the covariance matrix set the spread from the center. Changing the mean will translate model distribution, and changing the covariance will alter the geometry of this distribution. Similar to the Gaussian distribution, the Laplace distribution is also a continuous distribution. It's symmetric, centered at mu with a sharp peak and exponential tails. For a binary variable x, its value is either 0 or 1. To model its probability, we often use the Bernoulli distribution, parameterized by q, where q is the probability that x equals 1, while 1 minus q is the probability that x equals 0. When a categorical variable x has more than two possible classes, we model its probability using the categorical distribution as described by this equation. For example, when there are 5 classes, the model has 5 parameters, q1, q2, q3, q4, and q5. We can verify this equation. For example, when x belongs to the third class, the third element in x equals 1 and the rest equals 0. And we can verify that the probability is indeed Q3. A neural network is just another way to define P sub theta, where theta now means all the weights in the network. The network takes a sample of x as the input and generates its probability as the output.